Chapter 2, Section 10, Principal Stresses and Maximum Shearing Stresses. Course learning objectives. Still, this is the third one that is tracking down this big overarching goal of performing stress transformation so that we can understand the state of stress in a different coordinate system. This will also involve, and this is today's lesson, finding the maximum and minimum stress. Why do we care about that? Because that's where things break. When you have the worst case scenario, that's the maximum stress. Oh, look at that. This got left behind from lecture 2.6, so you probably need to ignore that on the previous lecture too. Equations that we've got for this time, now we're moving on, and all these equations have this little tiny p. Not all of them. But the reason they've got that p is now we've got a new term or a new idea that we're going to be looking at, which is the principal stress. So these are the 4 new equations from this section. All right, so let's start with where we are. We just finished the last section with these transformation equations. Excuse me. The transformation equations allowed us to take, if we had a stress cube, right, and we were pulling on it and we were pushing on it and we were adding some shear to it, we just had all kinds of arrows going on, right? That was our general state. We've got a sigma x, we've got a sigma y, and we've got a tau xy. We could plug that into this equation, sigma x, sigma y, tau xy, and for any angle out there, theta, which related the xy to some new orientation, sorry, we could calculate what the normal stress was on that plane. And we had 2 formulations for that, this one and then the double angle. We also came up with a transformation that allowed us to get the new shear on that plane. And we had 2 formulations for that. Well, now we're interested in calculating the maximum. So how do we do that? Well, let's keep going. We have these 2 equations that I want to focus on. This is the normal stress and the shear stress. The equation that I had for normal stress didn't have the sigma there, so I had to add it. But we want to try to find theta such that my normal stress or my shear stress is the maximum. How do we find the maximum and minimum? Well, I hate to tell you, but it is a bad word. It is calculus. If we have this equation, and if we want to find the maximum or the minimum, right, we're going to take its derivative with respect to that angle, and we're going to set that equal to 0, and then we're going to solve that. So that's what we're in the process of doing. Once we solve it for the angle, then we know where the maximum is occurring and we know the minimum is occurring. So buckle up, because this is kind of a, yeah. Once we've got the angle, then we can substitute that back into the function and we can get the maximum and the minimum. So do you remember what that function is? Remember what that function is? Well, I wrote it down for us. Okay, I cut and pasted it. There's our function. And so the first thing we have to do is we have to take a derivative. So what is d sigma d theta? Well, I was going to just skip this and go right to the equation, but it's not terrible. There are 3 terms up here. 1, 2, 3. And so if we look at each one separately, the first term is equal to 0. It has no functionality on theta. So that one I could do. The second one, you got to use chain rule. So it is going to be plus sigma x minus sigma y over 2 times, what's the derivative? What's the derivative of cosine of 2 theta? Well, here's where chain rule comes in. It's sine 2 theta, but I got to have a negative because the derivative of cosine is minus sine. So I put that out front. And then I've got to have a 2 also because I got to take the derivative of the inside. That's chain rule. So really that 2 and that 2 cross out. They cancel, to use math parlance. Okay, so I got that one. And then the last term is going to be plus tau xy. The derivative of sine is positive cosine. I'm still going to have that 2. So let me add the 2 out front this time, a little easier. And then a cosine 2 theta. This term gets cleaned up a little bit. It's a minus delta x. And I could put plus, but let's do it. Did I say delta? Sigma. Minus or a negative the normal stress in the x direction minus the normal stress in the y direction. Remember what those things represent, not just the variable symbols, but what they actually represent. And then a sine 2 theta, and then a plus 2 shear xy. All right. See if I can do this. Bonk. Cosine of 2 theta. It's all equal to 0. Yep. How'd I do? Well, if we look at the next slide, I actually did just copy it. Sorry. Set that equal to 0 and solve that. Well, if I set it equal to 0, really I'm just gonna move this term to the other side where it's going to become positive. So I'm going to get minus, oh, sorry, the minus went away. It's sigma x minus sigma y. Maybe we even want to refer to that as just the difference in the normal stresses times sine 2 theta plus 2 the shear in the xy. Sorry, I don't want plus. Equals cosine 2 theta. Okay, so just solve that for theta. Well, I've got sine 2 theta over cosine 2 theta is equal to tangent of 2 theta is equal to 2 tau xy divided by the difference between the normal stresses, the x and the y. So that's, can I solve for that? Yeah, I can come back. I can use that equation and I can use that to calculate an angle. In fact, that's the first one of those equations we have to know. I believe that's 214. So that's the first one of those equations that we have to know, and that tells us the angle at which we're getting our maximum shear stress. It looks like that, right? So that's good. Now the difficulty is that's our angle. So really what we have to do is then say theta is equal to arctangent of 2 times the shear over sigma x minus sigma y, and then that whole thing has to be divided by 2. And so now I'm going to take that and I'm going to substitute it into my transformation equation. Remember, my transformation equation looked like sigma in the n direction was equal to sigma x cosine squared theta plus sigma y sine squared theta plus, and it kept going, right? I had, hey, get rid of the ugly mug again, plus 2 times shear xy times sine theta cosine theta. So just take this arctangent term and plug it in there, and you'll be all set, right? That's a lot of math, and it's a pain in the neck. I've done it. I have done it, and I used to derive this in class, but honestly, it takes 40 minutes. It takes some trig identities. I have been skipping it the last 2 years. And what we get when we do it, we skip ahead. When you solve it, what you find out is that there are 2 principal stresses, P1 and P2, and they equal to the roots of the equation, and there it is. And that's equation 215. Now those are our principal stresses, and by principal, what we're doing, we're using that word. The principal is equal to the max and the min. Now we get a little more picky about that. Sigma P1 is greater than sigma P2. So when you start listing them, when you start telling me what they are, P1, sigma P1, since it's greater, it's got a positive sign, or it's more positive. It could be right, when you get to negative numbers, it could be the smaller negative number, but it's the closest to being a tension. It's the largest tension that's being seen. All right? That's important because tension is where a lot of these fractures are going to take place. So, but that's our equation. Now, that's pretty slick. One thing that when we skip doing all the math, we miss some things. Some of you would understand the equations better if I took the time to go through all the math. Some of you would really, I don't want to say you'd appreciate it, but you would understand things better. And some things show up differently, and because you spend more time with them, you start to see relationships that you didn't see before. Here's one of them. When we did our derivative, we got that equation. And what I want to tell you is there's something that looks familiar when you're going through it, and that is it's exactly twice the shear stress equation, the shear transformation equation. So what I'm seeing is I'm going to take, in order to solve for the principal stresses, I set that equal to 0. And if I set that equal to 0, that means that this has to be equal to 0 because it's equal to twice the derivative of the normal stress with respect. So when I have my maximum and my minimum principal stresses, which is what that's saying, my shear stresses are 0. My shear stresses are 0. So if I take this fancy little thing and I push on, or I pull on it, and I push on it, and I shear it, and I find an orientation where I've got that and that, and this is, if this is my maximum, because that's in tension, that's going to be my P1, and this is P2. If those are the principals, then shear is equal to 0. It comes out of the mathematics. We proved it, but we didn't prove it, but I want to point it out. I mean, we didn't want to spend, it's got to be an hour of hardcore math where I make a lot of mistakes and then you guys have to yell corrections, and we've all got masks on. It's just not going to be pretty. So we're going to do it this way again, but I want you to realize That comes out of the mathematics. All right? This sentence, that's the only change in the slide. There is no shear where I have the maximum and minimum normal stress. Now, we just solved this. We just did this for sigma, for the normal stress. Right? Now we want to repeat the process for the shear. So we're going to take this equation, right? And we're going to take the derivative of tau in the nt direction with respect to theta. We're going to set that equal to 0. No, we're not. Just kidding. More calculus. We're going to jump ahead to equation 217 where we get the answer. We have the answer right there. Boom. Done. And we can drop in. If we want to know what our principal shear is, we can drop in, and we've got X, Y. We know all of those things. If you remember the example problem that I just did on the stress transformation, I wanted you to write down at the very beginning, I want you to write down what's sigma X, what's sigma Y, what's my shear, and what's my angle. And but see, you can get the principal just right there. Boom, done. You can get the principal shear just like that. And actually, if we go back, or if we go forward a slide, you'll see that those things, those will lead us to the magnitude even if we don't know the direction. What's the next slide? Here we've got a slide which is giving us equations 215 and 217. Now, these equations are the principal stresses, the principal normal stress, and the principal shear stress. But what I want you to see is that this term here, the shear stress, the principal shear stress, is just that add-on part there. This could be rewritten. I could get rid of that and simply replace that with the principal shear. And that's important. That's going to help us in our next section imagine how some of these things are taking place and start understanding these equations a little bit different. In our next section, in section 211, I believe, we'll start dealing with another way of looking at these stresses to figure out how they interact with one another. But that relationship is taking place there, and that's a valuable one. There's one other equation from this section that I want you to know, and that ties back to the previous one, and that is the maximum and the minimum are only separated by that shear. So there's the shear stress, the maximum shear stress is the difference between my maximum and minimum normal stress divided by 2. Now, you also have to remember my maximum, this is in tension, so that's positive. This could be in compression, it could be negative. So you could actually be adding those together. All right? So, the equations from the study guide that we had to know. The first equation allows us to solve for the angle at which we have our principal stresses. It allows us to know the orientation of that stress cube as we rotate. It allows us to know how that changes. The second equation that we've got from this section is allowing us to calculate our principal stresses from the stresses that show up on that generalized stress cube, on that cube that looks like that with, right? I've drawn it how many times? I've drawn it a couple times. Oh, erased it without even trying. We can just take, if we know sigma x, sigma y, and tau xy, first we can calculate this. Second, we can calculate that, our principal stresses. That is the worst case scenario, the worst tensile stress, the worst compressive stress. We can also calculate our worst shear stress. And then there's some other information that I want us to have in our bag of tricks, but we really won't use it till the section on Moore's circle, which is next. All right? There is more to learn about this theta and this 2 theta trick, and it's showing up on this section of the slide over here that I've kind of been ignoring, but that goes to our next chapter with Moore's circle. So it was on the equation sheet where I copied it. It ties to Moore's circle more than anything else. The next presentation is example problem 211, where we will calculate the maximum principles, and we'll use these equations that we've just, I don't want to say derived, we skipped through the calculus pretty lightly, but we'll use those equations, we'll solve a problem, and we'll see how that information plays out for us. And then we get to Moore's circle, which to me is a lot of fun. I know it can be a challenging concept, but it's a lot of fun. So hope you're doing well. See you soon.